No. Okay, turn off. No. Okay, it's right. Got it. There we go.
Now Matt's not on the screen.
All right, so
Can I have the
Oh,
remote?
no, you're not on the screen as
Can I have
much.
the remote?
you're
Sorry,
going to share. It should say, just press any button on the remote.
Other way. We're backlit.
Oh, sure. So,
Hey, it's Jordan.
Hello.
Your camera.
Sure.
Let me see if this works.
they can see go constant presence as well.
See yourself.
Oh,
Usually we see ourselves.
Usually it's your, yeah, you want to turn it on?
That's coming on now.
Yeah.
Oh, okay.
Why isn't that on?
I don't know.
Blinking green.
On to infinity.
What?
So there should be 10 other people.
I don't know. It's got
Yeah, but it's not 2:30 yet.
Oh, they start right on time.
Yeah.
I'm not. So what do I do?
Where are you sharing content from? The computer?
I guess so. Go ahead.
Unshare that.
Whoa.
Do it again.
Okay, so
Nope. How do I get to this? Sorry, guys. We're trying something new here.
let me see that.
Yep.
Oh. Cool. Looks cool.
DVD maybe? No. Where's the HDMI plug in? Do I need to change an output on? Come on. Ugh. I feel like this is meant to be plugged into the DVD input, and it's not.
Well, everything's running from the monitor. I put the signal flow, but it should just.
You had to cancel class because of technology issues.
No.
I mean, I can have class. I just would really like to be able to use this little whiteboard thing.
Doing drawings in Google Docs.
How are we doing? We're still missing. We got Enia, Will, and Jordan. And the end. Coleman. We're missing Jasmine and Kaylee. I'll get attendance while I'm doing this.
Put the microphone closer to him.
No, I think you'll.
Did you say you were missing us?
No.
Okay.
No, we got you. I got you. No, I was figuring out who I'm missing. I'm missing Kaylee and Jasmine. And oh wait, here's some new people. Missing
Really dark.
Yeah, that's really.
Somebody who just joined. It's super duper dark. That's Trinity.
I was sleeping. Jasmine was sleeping. Don't judge me. I'm very tired today.
Oh, it's a thing of beauty. All right, Dallas, Langas. We are missing Peter and oh, did Limbo? He's not. Oh, there he is. Oh, Tay did that weird. Peter. Done. Me, Peter, and Peter. All right, no hope on that. Josh. Sorry, guys. We thought we had figured out a way to hardwire my iPad into the system so that I could draw on a whiteboard thing for you instead of my Google Drawings thing, but it appears like we have not fully troubleshot that.
I'm just gonna start unplugging things, and it all goes horribly wrong. Blame Mr. Taylor.
Oh God.
Try
Try
undoing your presentation and redoing your presentation.
So stop. Wait, no.
Oh, no, it's not at all on your computer.
Okay, that's back to normal.
Try doing your presentation again.
And you want me to hit the square button again? Nothing.
Try just drawing on your iPad, make sure it's.
Nobody sees a whiteboard with me drawing on it right now, right?
No.
All right. Well, we can yield, Josh.
I'll continue messing with it.
All right. Let me know if you figure something out. I'm gonna stop the presentation, and then we'll go back to my
Where's the camera?
slapdash.
Pointing it.
There we go. Okay. Insert prime. Okay. Where am I at? So I want to talk a little bit about energy and momentum today. Also, I want to decompress a bit. We had some heavier math in our most recent videos, and there's a couple things I want to say about that. Here at Hopkins, when I teach this course, our math requirement is Calc AB. So people haven't necessarily done much by way of integration by the time they get into the course. I still have done the integral derivation of relativistic kinetic energy for them, but I've never actually required that you be able to reproduce it for any kind of test or assessment. And so it's kind of offered up there because my math breakdown in my brick and mortar course has become more and more kids who are past calculus. And so I've gone for it. And I wanted to share that with you. If you felt at sea with the integration techniques and the things that I was doing, that's okay. I'm not going to hold you to it. In the end, all I really need you to know is that we have a new expression for kinetic energy that
I think
is.
you're sharing it.
Oh, sorry. Thank you, Karen.
No.
Share screen, Google Chrome, this window. KE is m naught c squared times, I will just write out gamma minus 1. We found it by using the work energy theorem. And the expression looks markedly different from the old one that you are familiar with, that is 1/2 mv squared. I quite recently put together for you and popped up online a video where I use Taylor series or geometric series expansion to explain how it is that at lower velocities, what you doing?
Go ahead and reshare from your computer, sorry.
Okay, do I need to?
No, you can just reshare from your computer.
Okay. Sorry, tech guy is trying to figure out what was wrong with the other thing.
No, I'm mostly just breaking stuff, sorry.
Oh, okay. He's just breaking things, just for our amusement. Okay. That through Taylor series expansion, the new kind of sophisticated version of KE decays to 1/2 mv squared as we would hope it would. Now, what I want to focus on here is the last part of that discussion where I said something pretty weird. I said that essentially, actually here, just to make things easier, I will just use, no, that's not going to work. Everybody okay if I use just Y to stand in for gamma? Okay. That if we wanted to play around with this equation, we could very quickly say that m naught gamma c squared equals KE plus m naught c squared. Just kind of arbitrarily say that, and then we could divide through by c squared. and get this very strange conclusion that the dilated mass that we talked about in our momentum discussion is increased from the regular old mass m naught to this new expanded dilated value of mass m naught gamma, simply because we gained kinetic energy. And then if I go ahead and I remultiply by c squared, like it's here, we could invent a new term called total relativistic energy, E. That is kinetic energy plus this thing over here, which I will label as being rest energy E naught. I'll just get an arrow going on here. Right. The total relativistic energy that an object has, it's kinetic energy plus its rest energy, and that something has energy simply by existing, equal to its mass times the speed of light squared. This is an equation that you have known for most of your life, E equals mc squared. The question would be like, well, why would we make that decision? Why would we arbitrarily rearrange this equation and come up with this new crazy value of energy when we had an expression for Ke? What's the point? Does anybody have any comments there? Why do this? Ini.
Wasn't that like it makes the energy and mass conversion theorem more like plain and visible? That like energy and
what
mass.
What do you mean by energy mass conversion theorem? What do you mean?
That like energy and mass are like the same thing. That mass like has energy and mass is a form of energy. And it, like she gives way to that idea, and that mass changes
absolutely.
Because energy changes.
What evidence do we have that this is worth doing, though? At this point, we've derived Ke rather rigorously, in my opinion, and then we've just arbitrarily rearranged it to this thing. And what you're basically speaking of is something that you know outside of the total progression that we've taken to this point to get here, right? You're aware of the equivalency of mass and energy. But what I'm talking about is a moment in history when somebody just posited this as a possibility, simply by rearranging the algebra. What kind of evidence could we have that this, what would we have to see to make this worthwhile? Jasmine?
I mean, the atomic bomb, you take that mass, you make massive amounts of energy with it. And that's what it was basically used for.
Okay. How?
By splitting the atom.
Okay. Where does the mass go? So hold on a second. Let me, I had everything prepared in my little thing, but I'll do it this way. So let's say that we had a big old nucleus. Well, I'll go with uranium-235, 92. So we have uranium-235 hanging out just randomly at some moment, maybe collides with another particle, maybe just randomly, which is something we'll get to by the end of this course. It decides to break apart into pieces. And let's say that it ejects from one side a helium nucleus, which is also known as, anybody know what a helium-2 plus nucleus is also called? It's okay if you don't. I mean, it's not something we talk about in class. What's that?
Alpha radiation.
Yeah, an alpha particle. Absolutely correct. Right? Like long ago, we knew about radiation, and we knew that there were these giantly energetic particles that we called alpha particles. It took a while to realize that they were actually helium nuclei flying off. So this uranium atom splits apart, explodes, and that helium nucleus goes flying back that way, and another nucleus that would be, according to the periodic table, would be thorium. Let's just make it 231 sub 90. These may be ionized in the process, whatever. So to conserve momentum, This is flying off in the opposite direction, and it has certainly less velocity. But if they have velocity, they have kinetic energy. So we have some Ke sub thorium, and over here we have.
Yeah, don't. Okay. You need to use
We got Canterbury.
Yeah,
Ke sub helium. All right. Now, to begin with, before this nucleus exploded, all we had was m naught uranium c squared energy. Let me make that a little bigger. But not that big. Now, what kinds of energy do we have? Let me make these bigger here. Now that it's blown apart, what do I have? I started with m naught uranium c squared, if we're going to accept this postulate that we had a rest energy of m naught uranium c squared. These two particles flew apart. They each had their own kinetic energies. What else is there?
The result.
Don't they have their own rest?
Yeah,
mass?
their own rest mass.
They have their own rest energies. So we have this sucker over here actually has, according to this posited assumption, I'll just go like this. Okay. We then grab hold of the thorium and helium atoms, perhaps with a magnetic field or something. We make them orbit around in a circle. We use centripetal force, and we determine the masses of the objects. So we bring them to a near state of rest. And what we're left with at the end is simply, when we've taken all the kinetic energy away, we have an m naught thorium, and we have, we have an m naught helium. And what did your chemistry teachers tell you is true about the sum of those two nuclei's masses? Okay, maybe not all of your chemistry teachers, but many of your chemistry teachers has said what about the sum of those two masses?
That they have
It's equal to the sum of the original mass.
Initial mass.
That it's equal to m naught, doing that, uranium.
Wait,
No,
just
it
a
isn't.
question.
Yeah, go ahead.
Should that be Ke thorium plus MC squared?
Oh, yeah, there's missing
Yeah, okay.
C, and I apologize, I'm missing something else. That should have been helium, right? Thank you very much. Okay, there we go.
On the other side, too.
Oh, yeah. There we go. And drop my V. Thank you, both of you. Okay. So we have m naught c squared that we suppose is rest energy. The objects explode. Right after they explode, they each have their own kinetic energies and supposedly these rest energies. We bring them to a halt. We measure the masses of the two daughter nuclei, the thorium and the helium. We add those two numbers together, and we hope, because we haven't destroyed any protons or neutrons, we have the same number of each of those, we hope that that sum adds up to the mass of uranium. And it does not.
Isn't it less?
Yeah, absolutely correct. The mass of these two nuclei combined is less than the mass of the uranium. Where did the extra mass go?
The kinetic energy.
It was the kinetic energy. It was equal to the kinetic energy these particles had after they exploded. And then eventually it went away to doing work to accelerate something else, right? When we stopped them, conservation of momentergy, that's pretty great. Conservation of momentum and energy would necessitate that it's not destroyed from the world, it goes off and does its own thing. So to make this equation correct, that's what I did last time. There we go. what do I need to do on the left-hand side to make, here's the rest energy that I started with, m naught u c squared. Of course, I need to get some c squareds in here to get my units working again. But in order to make this work, if this is all viable, what should I add over here?
Kinetic energy, the particles.
Ke, so I should add on Ke sub thorium and Ke sub helium. So that while mass was not conserved, as our chemistry teachers would have us believe, right? That they tell you mass conservation is something very, very important and that shouldn't be violated. That's not true. Mass conservation is a very nice lie. It's close to correct. In a chemical reaction, like burning some kind of hydrocarbon, there would be a mass change again as new molecules are formed. But the amount of energy involved in a chemical reaction is so minuscule that the change in mass of the object is essentially immeasurable. So we don't bother with it. When you're dealing with nuclear reactions, though, there's a measurable change in the mass of these nuclei as they are broken apart and combined together. The mass of the uranium part of it is taken away and it's transformed into kinetic energy. The question becomes, how much? Before I move on, though, any questions here? Okay, so this is always kind of the amusing part, all of this. How much energy are we talking about? So let's say that we did some experiment where in a set nuclear reaction, say we had a whole bunch of uranium-235 that we started out with an E initial of m naught c squared, and when we were all done, it was such that E final was equal to m naught minus 0.001 kilograms. Okay, so that in the process, the kinetic energy that was lost amounted to the loss of 1 gram. A single M&M, a paperclip worth of mass were evaporated from the world and transformed into kinetic energy. It would take many kilograms of uranium for this to happen, but I mean, we certainly could have a nuclear reaction in which an entire gram of mass disappears from our world. So that means that, and this is what Eni was talking about with our mass energy equivalence, that the energy generated is essentially equal to, I can't write it, delta M, that's all superscript, times C squared. So in that case, this is 0.001 C squared, which is, you think you figured out, Josh?
Is it? Oh, is it?
8. The whole world is gone.
That shouldn't be.
Yay! Can you all see again?
Yeah, we can see you the whole time.
Oh, really? Oh,
Yeah.
You just disconnected our television. Okay. That's fine. All right. So I lost screen. You were fine. All right. So C squared is, I guess at this point, my favorite number in the whole world, 9 times 10 to the 16th. So this is 9 times 10 to the 13th joules.
That's a lot of joules.
A lot of joules. That is a lot of, an M&M, if you took a single, next time you eat one, just like put the M&M in your mouth and be like, if this evaporated, hold on a second. Let's say that we evaporated the mass of 1 gram and we gave that much kinetic energy to an M&M. to a second M&M. We took all of its mass energy and we gave it to that other M&M as kinetic energy. How fast would it be going? Okay, so we'll say that the energy generated gets turned into Ke, and we have a new equation for Ke. Let's say it was given to a second M&M. So this is now 0.001 kilograms times c squared times gamma minus 1. Okay. I pick my numbers fairly conveniently, right? What does that make gamma? Remember, the energy I generated was 0.001 c squared. And this over here is 0.001 kilograms c squared. So what happens in this equation right here? Those numbers.
Oh, gamma equals 2, doesn't it?
Exactly right. The 0.01 kilograms c squared would cancel from both sides, which would give us that gamma minus 1 equals 1, which gives us the gamma equals 2, which means that the velocity is 0.87 times the speed of light. So if you evaporated 1 gram of mass and gave that kinetic energy to 1 gram of mass, it would travel 87% the speed of light. I just don't even know what to say about that. Obviously, you couldn't focus that energy to go to exactly one object, but it certainly puts in perspective what was happening when Oppenheimer and the other guys in the Manhattan Project set off the first nuclear bomb. What's the famous quote from Oppenheimer? Does anybody know?
I am become death.
I am become death. It's a translation from the Bhagavad Gita, which means I am Krishna, I am destroyer of worlds, I am the beginning and the end of time. And a more literal translation of that text, it reads as, I am the end of days, the end of all things. I have destroyed the world, is what he's saying. And I'm glad that we have lots and lots of international laws that prevent us from doing nuclear testing. But I also think it would be enormously powerful for us as a worldwide culture to keep a realistic view of what this energy is like. And we don't really do it anymore, or at least, other than some countries illegally doing it underground. We don't see these kinds of explosions anymore. We cannot conceive of this as being a real number of joules that man could have created in a single act, but it is. And that's what those locations, both out at Los Alamos and the places where those bombs were dropped, that's the kinds of energies that we're talking about. And our current nuclear technology that uses this mass energy conversion would generate far, far more energy than this. One thing that you might note here is that I've talked about nuclear fission. You have a nucleus, it breaks into pieces, mass is lost, energy is produced. In light of that, you've always heard that fusion produces more energy, right? But that can't make sense, because if we put the same two particles back together, shouldn't it take energy to do that? Shouldn't we have to put the energy back together? How could fusion produce energy? And there is an answer to the question. I wonder if you have any hypotheses as to what it could be.
Is it because they stop moving and that it comes out of the energy? Comes out of the kinetic energy?
Something would have to. That's the other thing that comes out of this. The energy isn't just some phantom. It's contained. It's contained somewhere. It could be in photons. That's true. But the kinetic energy is ascribed to some kind of particle afterwards. It really is that only fission can actually release energy. Mass has to be lost. Wait, hold on a second. Henry, is that right?
Well, I was just gonna try and answer, but I guess I must be wrong. But I was gonna say maybe 2 hydrogen atoms going into a helium atom kind of results in less potential energy of the system than does a U-235 splitting in 2.
Okay. When you've heard about fusion, what are the hydrogen atoms like that go into fusion? Jordan.
So, as I understand it, creating helium in a star in fusion does not involve 2 hydrogen atoms, but 4, and 2 of those protons become neutrons in the fusion. and that changes the quarks around that allows them to hold themselves together, and neutrons are slightly less massive than protons, and that mass is released as energy.
I wonder if I can call this up as an image. Solar fusion reaction. I bet you I can call it up as an image. The answer is, yeah, there you go. Whoa! The answer is that fusions and then fissions happen in the process. I just heard my hilarious noise back through your microphone, so that was funny. Right? It's not just two things get stuck together and then a new atom is produced and yay, energy happens. Stuff gets stuck together and falls apart, and stuck together and falls apart. And in the fission process, you see these little purple gamma rays here? There is released energy. There's some neutrinos being released as well. But there are fission processes in between that happen after the initial fusion processes in order for energy to actually be released. Just something that always bothered me when I first started learning about this. How could it go both ways? How could falling apart generate energy and coming together generate energy? And the answer is there has to be falling apart after the coming together. It also, I should note, that's kind of why it takes so much energy to get this to happen in the first place, because it's hard to get them to come together. You have to do lots of work to get past that first hurdle. Once you do, things chain reaction out and generate the energy that we would potentially someday use. So there you have it. Now, I made a little video on this next topic, but I want to make sure we're cool that you have a worksheet on energy and momentum coming up. And we will be talking about objects that kind of have a practical size. The kinds of objects that we actually accelerate to relativistic velocities in the real world on a daily basis, what are they? Because it's a second-to-second basis. It's all the time. We are accelerating objects to close to the speed of light. Give you a hint. It is not a donkey. It's not an apple. Not a piece of dust. I mean...
electricity?
What do you mean by electricity?
Like moving electrons through wires?
Yeah, electrons we accelerate too close to the speed of light on a regular basis. Protons, somewhat less regularly, but the Large Hadron Collider, right, and other particle accelerators accelerate nucleons, protons, not neutrons, nuclei, protons, electrons, tiny little subatomic particles or ionized atoms, the things that we can accelerate to these ridiculous velocities. We are not accelerating baseballs close to the speed of light. If we did, we would destroy the entire world because their mass would explode, their gravitational attraction would explode, and the whole world would be consumed. It would be a bad call, is what I'm saying. There's a great XKCD about what would happen if you were to throw a relativistic baseball. If I can, I'll find the link and I'll put it up in the assignment sheet. It's really, really bad. It's super bad. I believe the catcher, when he does catch the ball, which happens completely asynchronously, experiences a fusion reaction that causes him and like the entire stadium to vaporize, and then a black hole consumes the world. Anyhow, since we are going to be dealing with nucleons, we need special units, because if I wanted you to find the kinetic energy of an electron that were accelerated close to the speed of light, you'd be dealing with this. You'd be dealing with, the mass is 9.11 times 10 to the minus 31st kilograms times c squared is 9 times 10 to the 16th times gamma minus 1. I mean, it's not that you couldn't do it, but it'd be enormously tedious to keep track of these superscripts and to not mess up your minus signs, and you would get numbers that would be really small and hard to keep straight in your mind what their relevance is to what you're doing. So we want to come up with smaller units of mass, right? Like when you're dealing with finding the velocities of baseballs, et cetera, in regular physics class, you don't work in solar masses. You don't work in terms of the speed of light. You work in meters and seconds and kilograms because they're all on scale with the object that you're talking about, which makes the math practical for you to do. So we need a different set of units. How many of you have heard of electron volts as a unit of energy? Okay. Many, but not all. Okay, so let's say I had a pair of metal plates, and I hooked them up to a battery of some kind such that the top were charged up plus all over, and the bottom were charged minus all over. And I'm not going to make, if I had my little whiteboard thing, I put minus signs all over this bottom plate and plus signs all over that top plate. Okay. And let's say that I set these up such that there was 1 volt of potential difference between them. Has anybody not dealt with electrostatic potential in their regular physics courses? Voltage. Okay. How does voltage relate to potential energy?
It's potential energy.
Oh. Sorry, go ahead, Eni, you started, finish.
I said it was potential energy over the charge.
Yeah, it's potential energy, which you might have used PE, you might have used capital U. It's U over Q. If I put a single electron in here, not drawn to scale, with charge E minus, the electron charge, it would have a potential energy of, well, U would equal the charge 1.602 times 10 to the minus 19th coulombs. I'll spread that out just a second here. There we are. Times 1 volt, which is a joule per coulomb. That turns into 1.602 times 10 to the minus 19th joules. That's not a very nice amount of energy. So instead of doing all of that, we could say that that was 1 electron charge times a volt is 1 eV. So then an electron and 1 volt of potential would have 1 eV of energy, which is 1.602 times 10 to the minus 19th joules. If I upped the voltage to 20 volts, that would have been 1 electron charge times 20 volts, or 20 EV. If I made the voltage 10,000 volts and I put in a single electron in it, the energy would have been 10,000 EV. This is a very convenient unit for energy for a charged particle of this nature. So, where am I at? So let's say, did I use, yeah. Let's say that I had this electron, I placed it in a 10,000 volt potential, giving it 10,000 electron volts of energy. We could set 10,000 times 1.602 times 10 to the minus 19th joules equal to the mass, 9.11 times 10 to the minus 31st, blah, 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 kilograms, and solve for the final velocity. But we get really, really ugly as we did so. So we come up with a different unit for mass. And it's easy, but sometimes it's so easy that it has freaked my students out. Okay, so here it goes. We know that the rest energy of an object is its mass times c squared. We know that its mass, therefore, is its rest energy over c squared. If we knew its rest energy in EV, which happens to be 0.511, but I'm going to leave it at 0.5, okay? 0.5 million electron volts is the rest energy of an electron. I could divide 0.5 million electron volts by the speed of light squared, and that would be the mass. Are you okay? Now, show of hands, and I'm happy to receive either answer. How many of you want me to plug in 3 times 10 to the 8 for C and divide these numbers and get an answer?
What's the other option?
You want me? We got Coleman saying he wants me to just do it. Will, you're with me? All right. Kira asked, what's the other option? What's the other option?
Leave it. Just leave it
Just
alone.
leave it. Just leave it right there and say the mass is 1/2 of a million electron volts per c squared. Stop. The mass is 1/2 an MeV per c squared. And you're like, c is a number, Mr. Taylor. You can't do that. You can't just leave 1/c² in the answer. You can. Capital M, it turns out, capital M is a number. What number is it?
Million.
A million. I mean, an EV, you could say, is 1.602 times 10 to the minus 19th joules. You could say that a joule is a kilogram meters squared per second squared. These are all numbers. I can leave c squared there. And it's a really great way to do this. Why? Well, let's say that, now technically, I start out with potential energy and rest energy. Okay? And at the end of the day, when this thing accelerates across the gap, it turns into rest energy plus, obviously, what?
Kinetic energy.
Kinetic energy.
Now, when all is said and done, the Enochs all still cancel. And I'm left with U equals 10,000 electron volts equals KE equals M naught C squared times gamma minus 1. Using this unit for mass is freaking awesome. Why? Well, let me plug it in. Be careful with parentheses here. And what happens to the c squareds?
Drop out.
They are killed. Goodbye, c squared. Death. That's super nice. Writing my units as MeV per c squared makes that c squared term just go away. And notice, we don't have to multiply any horrible exponents by anything. We do have to remember that that 0.5 MeV is 500,000 EV, but that in turn leaves us with 50 equals gamma minus 1. Did I do anything crazy? I mean, I did things that were crazy, but no, I'm good, right? Oh, I put an extra. No, I'm good. Right? And now my answer for gamma is 51. By using that unit of mass and using that unit of energy, I made my arithmetic super easy. And that's a very important lesson about physicists. We're very good at math. We are very bad at arithmetic because we don't care. Okay, we just don't. We don't care about numbers that much. We pick unit systems to make our lives easy. You will find all different regions of physics that use completely different masses. Astrophysicists will use solar masses. They'll use light years for distance, as we were using earlier. But, engineers will use meters and kilograms. Some physicists will use what's called a CGS unit system, using centimeters, grams, and seconds instead of meters, kilograms, and seconds. And we will, for these kinds of purposes, use electron volts for energy and electron volts per c squared for mass. So just to check ourselves on this, the rest energy of a proton proton is 938 million electron volts, which makes its mass, I know this is a super easy question, but I'm just checking if you're paying attention here and got me on this. What is the mass of a proton? This is super simple.
That over c squared.
938 MeV over c squared.
Yeah. That's it. That's all you have to do is just add 938 MeV per c squared. Now, on your homework, you will have some questions that might say something like, say that a bunch of protons were given a kinetic energy. Actually, you know what? I'll go total relativistic energy. You're given a total relativistic energy of 93800 MeV. So E is 93,800 MeV, and it is a proton. What does gamma equal? Back. Sorry, let's come back to here. Take a look right here. E is m naught gamma c squared. So with that in mind, if I have protons with a mass of 938 million electron volts over c squared, and a total relativistic energy of 93,800, what is gamma, Jasmine?
101?
Just 100.
Oh, right, because we don't have the gamma. Yeah, okay.
If this were KE, it would have been 101.
Yeah.
If it's just E, this is just m naught gamma c squared. If it were KE, it would equal m naught c squared gamma minus 1. Okay? You will find that high energy physicists often refer to particles only in terms of their total relativistic energy, rather than dealing with kinetic energy at all. They just go straight to total, because then there's no minus 1. That is how lazy we are. Okay? We just talk about total relativistic energy. How about this? By what factor is this is a stupid question at this point, but that's the point of the units. By what factor is the mass increased?
Just 100?
100. If you were riding along on that particle, what would the length contraction of objects you pass be?
100.
100. If someone were watching, if you were a particle that if you were a proton, you had a certain half-life before you decayed into quarks, etc. For some reason, what would be the increase in half-life to somebody watching that particle fly by?
100 times.
So my point is just you can see why physicists would do this, because as soon as you say, oh, it's a proton, and its total energy is 93,800. Then you know gamma, and gamma tells you pretty much everything that you need to know to solve the rest of the problems, which is pretty handy. The last thing I'll say on this is I also ask you momentum homework questions. Now momentum, anybody remember the formula? It's pretty simple.
Mass gamma times velocity.
Yeah, it's almost what you thought it was. It's just gamma's approximately 1 for normal life. So it's m naught gamma v. Using these units, let's say, what did I choose for an example? Let's say I had a proton that was traveling with my good old friend 0.8 c equals v. And 0.8 c equaling v means that gamma equals 5/3. Okay, that's the 0.8 squared is 0.64, 1 minus, et cetera, et cetera, et cetera. Using these units, my momentum would be 938 MeV per c squared times gamma, 5/3, times 0.8 c. Now we could plug in for c, we could plug in 3 times 10 to the 8, et cetera, et cetera, et cetera. Or what could we leave our units for momentum at? Look at this carefully.
MEV over C.
Exactly. I just cancel one of the C's, and I'm left with, when you plug those numbers in, you get roughly 1250, you do that right? MeV per C as the momentum. By the way, if we didn't include gamma, and we just assumed that that momentum equaled M times V alone, we would only get 750. So gamma is pretty important here. I mean, obviously, it's 5/3. It's right there in front of you. But so there you have it. So on your next homework sheet, I give you a problem. The first one is ABCD, and I give you an object. I give you the SI units in kilograms, and meters, and I ask you to find the momentum and the energy, and you're going to punch around with your calculator, and you're going to get super mad. And then you're going to redo the exact same problem with these super awesome units for cool people. And you're going to see that life is a lot easier using these things. Anybody freaked out about the MeV per C squared or not plugging in? Is this confusing at all? Yeah, energy.
Do you have a specific, like, maximum number of significant digits you want us to use?
That's a good point. Not particularly. You know, on the homework, when you look at my solution set for homework worksheet 1, which I have made up, I haven't put it in because I need a couple more of them. You'll see that, you know, when gamma is truly large, in order to solve for V, I had to put lots of significant figures inside there just to get the point across. Like, you know, if the original number was 0.999 C and the eventual answer was 0.9995, I want to get the point across that it was different, I would include that 5. Sig figs, don't worry about them too much. Just make sure you get your point across. Infinity is too many. But generally, you know, if we're talking about your eventual test, it should be pretty clear. And I will say to you, like, you know, because I will have done the problem carefully in advance. I'll be like, give me 8 decimal places, so that, you know, it'll be clear that you need to go that far before you see a 9 stop repeating. You know what I mean? Mm-hmm. Why don't I care that much about sig figs? It's not out of a disrespect for significant figures. It's more because as an experimental physicist, instead of worrying too much about significant figures, I worried a lot about giving appropriate ranges of error around a number. So instead of simply truncating a number to a certain decimal point, I instead, you know, work to give an accurate range around some mean. So that's why I grew to not care that much about sig figs, and that's why my chemistry colleagues get mad at me. But you know, it's okay. So if it's relevant on your test, I will be clear. Does that answer your question? Okay.
Yeah. I also kind of had another question about rest energy. Sure. Like what? I mean, basically, what is it? Is it just the potential energy?
It is. I mean, it is kind of a form. It's like a form of potential energy. It's hard to get all of it. When you combine two nuclei together, there is an increase in the nuclear potential energy, and that increase in potential energy does manifest itself in an increase in the rest energy of the uranium atom. But never is a strong word. It would be very difficult to get all of that potential energy out in the form of kinetic energy or photons. That being said, the current model for the life of the universe as we go forward is that eventually all of that rest energy will someday fall apart into photons. And the sad thing about that is that photons don't interact with one another. And as a consequence, there will essentially be nothing. We'll come to a point in the universe where we will not be brought back together in a big crunch. What we'll do is disperse into a gas of photons that will never interact, and there will be nothing. No thought, no people, no planets, no anything for a long, long time. So yeah, it's potential energy on a short time scale, hard to get all of it. So we don't always think about it as potential energy. We think about it as just being like the energy of having mass. On a very long-term, many lifetimes of the universe so far scale, it would eventually be realized that potential energy had turned into kinetic energy. Sorry to continue the rant, but you just reminded me of a super important point. Any more questions on that before I make one more point?
Was the units for mass, was 1/2 a part of the unit, or was that just specifically for what we were doing?
Where,
the new units for mass?
Whereabouts? Are you talking about?
1,000,000 electron volts over c².
Oh, you mean, okay. I think I understand what you're saying. Back before I changed this to a proton. When this was an electron, I can spell words. The mass of the rest energy of an electron is 1/2 an MeV. So the rest mass of an electron is 1/2 an MeV, 1/2 an MeV per c². The rest mass of a proton is 938 MeV and has a rest mass of 938 MeV per c². So is that the 1/2 you were talking about, the 0.5 that was here before?
Yes.
That's just the amount of MeV that an electron has. Okay. I try to be good in the assignment sheet and say it repeatedly. If I'm talking about an electron, hey, by the way, don't forget, rest energy is 1/2 an MeV per c², or 1/2 an MeV. Okay. Now, fairly soon, we're going to be starting our development of the quantum model, and this is really, really important for that reason. What do you know about Einstein and quantum mechanics? What have you, Eni?
Einstein said that God doesn't play dice with the universe.
Okay. Other things. That
Einstein was.
Go ahead.
He was his theory, gave birth to quantum mechanics, but he sort of disagreed with it, while he was alive.
What of his explorations is credited with giving birth to quantum? Jordan?
He examined the photoelectric effect and proved that in order for this specific phenomenon to occur, light would have to be quantized.
Absolutely. And he didn't hate all of quantum mechanics. And he's actually responsible for a lot more of it than just the photoelectric effect. He wrote a lot of stuff that was later adapted. He just hated that he wrote it. And eventually ran into problems where he refused to accept the conclusions of quantum mechanics and got stuck. And the end of his career wound up being very sad as he was left behind because of a strict refusal to adapt. But you're right, the photoelectric effect. I don't know about you. I mean, a lot of you guys seem to have studied some of this in the past, but doesn't it feel weird? In 1905, he publishes the photoelectric effect papers. In 1905, he publishes the relativity papers. This one, photoelectric effect, Nobel Prize. This one, relativity, no one accepts for 50 years. But also, if they were published at the same time, didn't he have to work on them at the same time? And if he worked on them at the same time, didn't they go together? I mean, shouldn't they be? I mean, is that how you? Well, I guess you do, because you're in high school, right? You're writing an English paper and doing your math homework over here, and then you're playing soccer at the same time. But if you were a professional physicist, would you be like, I'm going to work on the photoelectric effect and relativity, and they're completely unrelated? They're not unrelated. What's a possibility there? Here's his equation for the total relativistic energy of an object. What button could I press on my computer right now to just suggest something super weird? What's that?
Delete.
Delete. or 0? Could there be objects that only have kinetic energy? That have no rest energy?
They have no mass.
They would have to have no mass. Well, hold on a second. That's a problem because KE is m naught. Well, that'd be 0 times c squared. This is just pointless. Why am I even bothering? Times, oh wait, gamma is infinity. What's 0 times infinity?
It's not always 0.
It's something. I mean, it could be 0. It could be banana. It can be any number, anything. It could be banana. I'm not. Okay, it's 0 divided by 0 is anything in the universe. So this could be something. And if you remember from, I don't have a Greek letter nu, so I'm going to use a V. To Einstein, what is a photon?
Massless?
Okay.
Just like a packet of kinetic energy?
It is kinetic energy. It is an object traveling through space that just is kinetic energy. And when it strikes another particle, it gives it kinetic energy because it is absorbed. And the photon disappears from the world, and the charge that was struck with it is like... And so I believe that it was very much his work in relativity that leads him to the conclusion, hey, photons, light is particles, man. Light is particles, and they are just little bundles of kinetic energy. And then the experimental data is what will eventually tell him it appears that the energy of these things is related to the frequency, which kind of means they're particles and they're waves, because if they have frequency, oh boy. Interesting. Apparently we have a dual-natured object, and then later, apparently everything is dual-natured. But I think it's really important to see that there is a connection here, that Einstein wasn't thinking about two completely disparate ideas, that in fact his work was next to Max Planck on blackbody radiation, what Max Planck discovered about the energy of photons. He had a resonant moment as he looked at his equation here and decided that this thing could be just declared to be 0, and that an object like a photon could be simply KE, existing in the universe on its own. It is also why we can have massless particles that have momentum, et cetera, et cetera, et cetera. All right. Anybody worried about this unit stuff? There is a video. 2 notes. I'm about a third of the way done. I'm trying to plug through those homework sheets. A lot of good work. The only things that people are really getting wrong are getting things reversed. And I'm trying to make really careful comments about that on the sheet. As I said in it, there's a couple of questions I designed to be confusing, and I make comments on that in there. And I wanted to showcase what the confusion with relativity is. It's not the math. That's not hard to do. Expressing yourself is hard. Deciding what each thing is hard. Okay? The math, not hard. One thing I noticed, a couple of people who filled out the worksheet, they highlighted something that I screwed up and made a comment, and I think thinking I would get that comment. And of course, once you've made a copy of the document to work on, I'm not shared on it yet. So there's one thing I screwed up. I changed the velocity in one of the problems to 0.8c to make the math easy, and then I didn't notice that later on it was still 0.9. So some people solved the problem with 0.9, some with 0.8, and some people noticed and put a comment. Next time, put the comment on the assignment sheet or email me, because I could see from when the comment was made, it would have been caught and it would have saved people some consternation. So I apologize for the mistake. And if you notice something like that, contact me or comment on the assignment sheet. Thanks, guys. By the way, this is 20% through all of the time we have together. This was the 5th of 25 classes, which is insane to me. Thanks for hanging with me. We'll talk more. I want to debrief next time as to if things have been too intense or it could be, even more intense on videos. And I think there could be kind of individual answers there. I'm sorry for keeping you over by a minute. Let me know if you have trouble with any worksheets. I'll see you on Friday.
Thanks.
All right,
Okay.
bye.
Log out. we're gonna test this while you're still on your computer and see if it works.
Okay.
Go ahead and try. I didn't want to test anything during class. I didn't want to take away more class than we already had. But if you want to start the presentation from.
We're just trying to figure this whiteboard thing out. Oh! Do you see it? Do you see the whiteboard? Muted? Maybe he's logged out.
He's muted.
Oh, he's muted. Okay.
I don't know.
Oh, that would have been so much better. Oh, wait, no. Wait.
But I don't know if that's local or if it's.
Wing!
Oh, wow.
That would have been so much better.
But can we see it here? That's the thing. Go back to Blue Jeans here because you should see this as a presentation.
Limo, can you see that, the whiteboard and those nuclei? You're muted. Can you see those?
Can I see what?
Can you see a whiteboard with some pictures of nuclei moving around on them?
I don't think so.
Thank you. We can see it here, but it's not getting out to you.
So is it just connected to the TV?
Yeah, it's just connected to the TV.
All right, well, that's progress.
No, it's... Also, you know.
Keep it all on. Go ahead and stop recording.